Okay, so let us continue where we left off. And in the last lecture, we were talking about the neuron and action potential. And now I want to talk more specifically about what happens at that synapse. So just a little point of review, when we were discussing action potential, I think there was something I failed to mention down here. So action potential simply means that a neuron has the potential to act. They either fire or they don't. That's what I refer to as all or nothing. Sodium and potassium are critical in this process. And another important phrase is what's referred to as an absolute refractory period. And what this means is basically that the neurons have to rest, that they can't constantly stay in, they can't constantly stay fired, but they have to rest. I can't think of a really good example off the top of my head to sort of illustrate that. But okay, so, but as I hinted at before, that it's really the synapse, it's really the space, between the end of the axon and the term and the dendrite on the other side. That's the sweet spot. That's where all the magic happens. This slide here has a bunch of terms, but before I get to the terms, I just wanted to start with sort of the drawing, right? And I'll explain it a couple different ways. Sometimes some students get it, and that makes sense to them, and others are like, you don't make any sense to me at all, lady, please try again. So I'm going to try to explain it in a couple different ways, using metaphors and not. But the idea is that, again, you have the electrical signal that travels down the axon, and then it causes these chemical molecules to be released in the space between the end of one neuron and the beginning of another neuron, and that's the synapse, or sometimes it's called the synaptic cleft. It simply refers to the space in between. So this is an illustration of the chemicals. When we talk about chemicals, we're talking about neurotransmitters. Neurons, the transmitters within the neurons, right? And then we'll get to all those different ones in a couple other slides. Some of them you're probably familiar with. Like dopamine is a neurotransmitter, serotonin is a neurotransmitter, oxytocin, cortisol, all of those are brain chemicals. Okay, so you have here in this circle here, what would be called a vessel. And in the vessel are molecules of brain chemicals, molecules of neurotransmitters. In this case, you have the presynaptic cell, and that's the one that's sending the messages, and the postsynaptic cell, that's the one that's receiving. The presynaptic cell has been, it's been charged, it's got the electrical charge, and it pushes those molecules out the synapse, and that's what is represented here, is all these molecules of neurotransmitters get released into the synapse. They float across to the other side, and they bind. When they bind in the next place, then they carry on that electrical chemical process again, and it continues moving on. They bind, and then they release, right? They do their little piece. An analogy is often a lock and a key. Not all molecules can fit into any receptor site. So this little green thing here, these represent the receptor sites. The red things are the molecules float across, they bind in the receptor site, they open the lock, and they're released, and then they go back up. Or they continue, or maybe they float across and they try all the locks and they don't fit into any of the locks, and in which case they go back up. And this is what's happening in these little blue shapes here. This is called reuptake, right? So you have vessels, neurotransmitters float across, they bind in a lock, or they don't, and then they're reuptake. They are reuptaked or reupsucked, as I like to sometimes refer to it, because your body wastes nothing. If there is not a place for that chemical to bind, we'll forget it, we'll just recycle it, and we'll use it later. So this is really important. Another analogy that I like to use is kind of like, because when we start talking about things like mood disorders or things like drugs, prescription and non-prescription, understanding this process is going to be really important. Because, for instance, if your brain is making a certain amount, let me see, this one is serotonin. So serotonin is for mood, right? if you take an SSRI, which is referred to, which means a serotonin reuptake inhibitor, such as Prozac, Fluoxetine, Lexapro, what's another one? Some really common antidepressant medicines. What they do is they prevent this reuptake, this recycling, and they force more serotonin to stay out here in the synapse to be used. So let me use an analogy for you. And if we were in a big space, you know, I'd be walking all over the room and pointing people out. But you can think of this kind of like a, what's the word? A cove, right? So maybe if you go fishing or boating or something, a cove. On one side of the cove, you have somebody with baskets of bananas and baskets of Brussels sprouts. On the other side of the cove, you have somebody who likes bananas and somebody who likes Brussels sprouts. The neurons, the neurotransmitters, the chemicals, are kind of like the bananas. So you throw bananas into the cove, they float across to the other side, and your friend goes and picks out the bananas and they eat them, right? The bananas get used. Well, every day you throw out the same number of bananas, and every day your friend happens to eat them on the other side. Well, one day your friend is not there to pick up the bananas, right? So the bananas are floating around the cove, and eventually they float back to you and you pick them back up. That would be sort of the analogy of the reuptake. You're recycling them. Well, fine, I'll put them out there for next time, right? I'll just throw them out tomorrow if there's nobody there today. Well, in one of these days, then you get this cache of extra bananas, and you throw in double the bananas that you threw in the day before. And this happens 3 and 4 times. Your friend on the other side is like, dude, I can't eat all these bananas. I can't eat all these. So he goes and gets all of his friends who also like bananas. Well, now he's got 10 friends standing here to eat all these bananas that you keep throwing in. Well, for the first few days, you're able to throw in enough bananas to satisfy his friends. Well, eventually you run out of bananas, and his friends over here are like, they're getting kind of grumpy because you called me over here to eat these bananas, and now there's not enough, and now we're hungry, and now we're mad because there's not enough bananas. What happens with things like these antidepressants is it blocks this reuptake. So an SSRI, I'd write it on the board, selective serotonin reuptake inhibitor. It inhibits, which means to stop. It stops the reuptake. So it's kind of like if you're to throw all these bananas in, or it's kind of like instead of me picking up the bananas that float back across, I let them stay in the cove, and I let more bananas float around out there. And eventually, when there's more serotonin in the synapse, because you've stopped it from being recycled, so instead of being on the other side of the cove, picking those bananas out of the water, you're just going to let them float, and they're going to go back over to your friend and back over to your friend, and eventually your friend's going to go get their friends because look at all these dadgum bananas over here. As those bananas float around, or as those molecules float around over here, your body's going to say, oh, we're not going to waste this, and your brain will create more receptor sites. It's like they went and got their friends to eat more bananas, but more receptor sites will be formed to use all this serotonin. If you've ever taken an SSRI, and I speak from personal experience here, the first 2 or 3 weeks, like, dude, you feel really good, right? Because I hate not having a chalkboard to point to. Maybe I'll get one my next order. But as you're blocking that blue part here, and you're inhibiting more bananas from floating up, or you're inhibiting more serotonin from being recycled, it means there's more out here. Yeah, and more serotonin is going to make you feel better. But as there's more serotonin out here to make you feel better, oh my goodness, now there's going to be more receptor sites. There's going to be more friends on the other side. And if you stop, this is why you shouldn't stop for 6 weeks. When you stop taking that antidepressant, there's no more blocking. Now you've got those serotonins going to float back up here, but you got all those other people on the other side, and they're wanting more bananas, and now more bananas are getting recycled and taken back up. So I hope that makes a little bit of sense. But what happens then is your brain makes more receptors to receive that more serotonin that was out there. There's more bananas that were out there, but now there's not more bananas out there because they're being recycled. They're being reuptaked. So that's why in the beginning it can be a real challenge to get adjusted to a sort of prescription. This is more of the same. I'm going to go over my 10 minutes here because I want to make sure I discuss or describe what's going on. And basically there's just multiple images of the same thing, but I wanted to show you in different ways. So this is an example of the same thing. You have your vessels that hold your molecules up here. They're floating across. They come to the cove and you throw them in. They're floating across to the other side and they're binding. In this case, what's this one? This is an SSRI, a selective, and the reason it's called selective serotonin is because there's lots of different serotonins. But in this case, it is a Prozac, a Paxil, fluoxetine, and it is blocking the recycling. So instead of these extra molecules going back up and being recycled, it's sitting here and it's blocking it so it doesn't get recycled, right? This is another image of the same thing. This would be serotonin, these little molecules. And it's important that I stress here that not all molecules can fit in all receptor sites. It's a lock and a key analogy. Some keys can go in lots of locks, right? But some keys cannot. So some receptor sites can receive more than one molecule, but in some cases, certain molecules can only go in certain receptor sites. And I'll talk more specifically when I get to the discussion about neurotransmitters. So serotonin floating across and binding in the receptor sites. They open the lock, sometimes they flow back. Another image of the same thing, except what this one does is it takes us developmentally further back because the brain chemicals have to be metabolized from what we eat what we eat. In this case, it goes all the way back to tryptophan and 5-HTP, which actually is it's an amino acid. And you can buy it if you have a fancy health food store. We don't have one anymore in Manhattan, but you can buy 5-THP, we used to be able to, over the counter in a health food store. And it's supposed to metabolize into making serotonin. But here's the thing, you don't want to take 5-THP and an SSRI because in fact, you can get too much serotonin. You could actually overdose. There's something called serotonin toxicity. So this is tryptophan, it becomes serotonin, it comes up to the cleft. I think in this case, they call it a synaptic cleft. It releases the molecules, the little red ones, they float across to the other side. In this case, you have a reuptake inhibitor illustrated in the blue, and it's gonna bind right here so that these serotonin molecules cannot go back up, but they have to stay in the synapse and they have to bind. So it's kind of like somebody standing on the side of the guy throwing the bananas in and saying, I'm not picking them up. You just go back across. Somebody over there better pick you up. Okay. This is another image of the same process, right? So this time you can see the presynapse. That's the one that's sending the chemical. You can see the postsynapse, the one that's receiving the chemical. Here, what's this one? This is I think these are supposed to be dopamine, probably dopamine, because in this case, instead of it being Prozac or Paxil, it's cocaine. And this is interesting when we start talking about drugs. When we talk about illicit, legal versus prescription drugs, is they all do the same thing. Some of them are just you can legally have and some of them you can't. In this case, cocaine is acting just like fluoxetine does to block the reuptake. and it's blocking the reuptake of dopamine. Dopamine is a really great neurotransmitter, makes people feel really good. It doesn't sit here very long. So just like these neurotransmitters don't necessarily sit down here in the locks very long, the blockers don't either. They'll sit in they'll block the reuptake for a period of time. I think it's like 20 minutes when they talk about cocaine, and then they'll float away, and then those dopamine receptors will go basically back to normal. So if you ever talk to anyone that, or know anyone that talks about cocaine, it's a very short, the high is quite short. And that's because the cocaine molecules sit in these synapses for a really short period of time. All right, I'm going to stop right there. I've gone over my 10 minutes, and I will wrap this one up.